Now, of course, this problem can be more interesting if we consider other components, such as what? Such as friction. Now, kinetic energy and potential energy, you know, you can always, there's always these two. If there's no kinetic energy change or there's no potential energy change, there's basically no motion. No, especially kinetic energy. There must be change in kinetic energy, otherwise there's no motion. But for the total work, we only consider this external force. As you know that there are other types of forces that we can also consider, such as friction. In reality, there is always friction. And for this example, when the pendulum actually spins, you may consider that at the hinge support, there may be some friction. And that's actually the real situation in our world. There's always friction. So one case you may want to consider is to consider that there may be some friction at this hinge support that can actually reduce the application of this moment. In that case, the work produced by external forces will be less than 15 pi. And that is the case when you consider friction. In this case, we do not consider any friction. Therefore, the work produced by the 30 Newton meter moment is just 15 pi. But if there's friction, this 15 pi will become smaller. Again, we consider there's a horizontal bar, and on this horizontal bar is a 6 feet. For its length. Now, at the free end of this bar is connected with a vertical spring, like this, and the vertical spring is sitting on some sort of support. So the other end of this vertical spring will be kept at this level, which means that the spring can only be stretched in the vertical direction from this point downward. And this point can never move vertically. Horizontally, you can certainly move. And this length, the stretched length, as we know, is 4 feet. Now, but this 4 feet is not the unstretched length of the spring. The unstretched length of the spring is 2 feet. Now we know that at the moment, this bar has a weight of 50 pounds. Now, at the moment, when the bar is positioned in this horizontal position, there is an angular velocity. Omega to be 2 radian per second. Like this. And so what's the question? The question is, because this spring is not going to stop this bar from moving, which means that at this moment we have an angular velocity 2 radians per second. We want to know that what happens when this bar goes further down below at 30 degrees. What happens to the angular velocity when this angle becomes 30 degrees? So that's the problem. We have to find out what is the omega. So if you may call this omega 1, and what is omega 2 when theta is 30 degrees. And that is what we are looking for this problem. Okay. So how do we solve the problem? Of course, you must have the spring constant, and the spring constant is 6 pounds per foot. So the spring constant here, K, is 6 pounds per foot. Now, first of all, we have to understand this problem by what? By knowing that the position when the spring is unstretched is not like this. So that means at this point, you already have the spring force acting like that. Therefore, it is of course important to know that what is the unstretched, what's the depth, what is the amount of spring force acting at the free end of this bar. So we may want to determine what is the spring force. First, what is the spring force? What is the spring force acting at here? You know that spring force is linear with respect to displacement, right? And slope is a spring constant. Therefore, when the displacement is 0, spring force is 0. However, for elastic potential energy, we do not just use the value, we use the integral, which means you have to find out what is the area here, and that is why elastic spring energy equals to 1/2 of K times S squared, which is essentially this area. However, for this problem, we have to be careful here. We are looking for the elastic potential energy, not from 0 to here, a given displacement, because when the bar is at this position, remember what I said, this 4 feet is not the unstretched length, which means the unstretched length is 2. That means if you look at the displacement for the spring initially when the length is 2, it has no any displacement. But from 2 to 4, it's like this. So you have to remember that the stretch length is not 4, but it's 4 minus 2. And that means you have to calculate this area. When it's 0, that corresponds to 2 feet. And when it's 2, that corresponds to 4 feet, like this. So please do not use just the 4, you have to use the change of the length. And secondly, if you are curious, how do we know what is the position of this bar when there's no spring force attached to it? Now this problem, you can solve it easily by recognizing this fact. So from this point here, from here to here, we have this to be 4 feet. From here to here, it's 6 feet. And that means when this spring is unstretched because of the boundary condition, the bar can only move something like this. And to some point here, this is the unstretched length. When the spring is connected to here, we have 6 feet here, and also this length will become 2 feet. And this means this is the initial position of this bar. And that's before you introduce any spring force to the bar, which is also the position when the spring is unstretched. Now, mathematically, of course, if the problem is changed to be, what will be the initial position of this? Because that's the moment when the omega not to be 0. So if you want to know how to solve this, and of course, this is a geometry problem. We know that for this triangle, this length is the square root of 6 squared plus 4 squared, and that is 7.211 feet. So that is this triangle, which is this triangle, from here to here to here, which is 6, 4, and 7.211. Now the outstretched position is neither these two, but is something in between. That means something here. Therefore, mathematically, we are basically looking for this problem, trying to solve this geometry problem. You have the spring to here, and the bar connects to here. Bar here is 6 feet. The outstretched length for the spring is 2 feet, and we know that from here to here, this is 7.211 feet. So we have 3 dimensions. To begin up,